All right, what's up, everybody? My name is James White, and today we're going to be going over the Fibonacci and Lucas numbers. I do want to prioritize the Lucas numbers. I think they're better, but without Fibonacci and the Fibonacci numbers, we would not have the Lucas numbers, so they have to get some credit too. So, starting here, all right, there we go. We're going to go over Leonardo of Pisa. He's the one who started it all. This man is from Italy. Also, his actual name is Leonardo Bonacci. He was born in the late 12th century, and he published many books. He published in algebra, geometry, trigonometry, and through his work, he earned the title of the most talented Western mathematician of the Middle Ages. And it is pretty unanimous from what I've seen. But his most famous book is the Liber Abbasi, which is the book of the hour, the one that we're going to be going over today. This book was created as a book of calculation. It was to help common people with all types of calculation. We're talking tradespeople, people for problems for area, regarding livestock, stuff like that. Um, however, but this book used the Hindu Arabic numeral system, which was the first one in Europe. So he pretty much brought the new number system into Europe. And what better way to get that started than creating a book that everybody can use? So everybody got a taste of the Hindu Arabic numeral system. So we can thank him for that. But the problem from his book that we're going to go over is the rabbit problem, which proposes that there are a pair of rabbits at the end of a pair, second month, they can reproduce another pair, and this rule applies to the new pair as well. So, barring any deaths or real circumstances that you would see in the world, how many pairs will there be by the end of the year? So, the answer is pretty simple. Of course, you can brute force the calculation and it wouldn't take too long. So, for the first 2 months, we have our first pair. The third month, that's when the second pair is introduced because the first pair can actually reproduce now. So by the fourth month, it's still only the first pair introducing another one, and it adds up and up and up. Going on, you'll see more pairs being able to reproduce, and the total does add up very quickly. And we can see this here on the image on the right. For the first 2 months, we just have one pair of rabbits, and it quickly grows. Um, so the final answer is going to be 233 pairs, but the answer does have a very nice recurrence formula to it, which we know as the Fibonacci sequence. This is a very famous sequence that adds the two previous terms in the sequence to obtain whatever term you're going for. As you can see, f of n equals f of n minus 2 plus f of n minus 1. Um, this formula is very famous, has gotten put to use all over, especially in number theory, but it's seen in many aspects of our world as well, as it's naturally found, as we can see with the problem before. Um, but the thing about this sequence, it wasn't really touched or analyzed for hundreds of years after its surfacing. We can thank our guy on the next slide here, Francois Edouard Anatoly Luca. We're just going to call him Edward Lucas because we're not French and we are American. This is the man of the day, the man of the hour. He was born roughly 600 years after the Liber Abbasi was published. Um, he had the typical upbringing of most until his early 20s when he had to go into the Franco-Prussian War. He was drafted as an artillery officer, but thankfully, thankfully France rose the white flag, and we got him back into what he needed to be doing, which was playing around with numbers. Um, it didn't take him too long to find his talents in number theory. He mastered primality methods that we still use today, which we see with Mersenne primes. Um, to this day, he holds the record for the largest Mersenne prime found by hand. This took him 19 years to prove. And I don't think that title will ever get taken from him because now we have computers. That's what's going to be finding those prime numbers. And he did a lot of work regarding number theory, but we're going to take a step away from that and we're going to go on the Fibonacci sequence, which is what he analyzed. And we got all of our awareness of it from Lucas. So, starting his work on this sequence, he did find a bunch of identities and theorems. We have three shown here, um, but beyond the theorems and identities that he found, the main piece of his analysis that really stands above the rest is finding the limit of the succeeding terms. So if you take one term over the previous term, it and take the limit of that, it gets to the value of 1.618, blah blah blah, keeps going, and that is known as the golden ratio, or phi. And this ratio tracks all the way back to Euclid's Elements, which is the problem for Euclid was it was a line being divided into two parts, and the longer part divided by the smaller part is equal to the total line being divided by the longer part. So they equal the same ratio. That number is 1.618, the golden ratio, something that is known as a divine proportion. And today it's also seen as a symbol of beauty since it is divine. And he did find many more theorems and identities. These are just three of the main ones. Easy to follow too. So taking this divine ratio of phi, Lucas, was playing around with it, and he took the powers of phi, and we get these values here. So taking it to the zero power, you get 1. I say round it to the nearest integer because that's what he does. Going to the first power, you get 1.618, which is the value of phi. Rounded to the nearest integer is 2. Going up, we get to 3, 4, 7, 11. And if you're seeing the pattern, the next one is 18. Then it goes to 29, and it keeps going. And these values here, these integers that he rounded to, are known as the Lucas numbers. They're a set of numbers that satisfy the same exact formula as the Fibonacci numbers, which is that recurrence formula of the succeeding terms. But there's no question in my mind that these are a better set of numbers than the Fibonacci numbers. These, in my mind, are naturally found, and they have an actual reasoning behind them rather than, the made-up scenarios with the bunnies, where you can just find a formula that applies to it. It was something that was discovered rather than created, and I think that is properly said to be divine. Now, looking at these integers I do have listed, they are in order of the phi analysis with the powers. And you might have noticed that there is an issue with them because the recurrence formula, if you add 2 plus 3, you don't get 4. But Lucas didn't really care about that. He just flipped the 2 and the 1. Everything was solved. Voila. And these numbers here, they'll follow pretty much the same identities and formulas as the Fibonacci sequence. So we can continue on with that. So taking a step away from the actual math behind them, these sequences appear in our world all over. They're seen in biology, geometry, computer science, finance, and much more. But these are the main focuses, and we're going to continue onto those topics. So looking at these sequences visually, we have a very famous image, which is this Nautilus shell here. I believe it's done very well. It perfectly resembles the sequence. It takes the areas of the Fibonacci or Lucas numbers as a square and stacks them up, and you end up getting that spiral. My guy over here on the right, he looked pretty cool, and he moves, so I added him too. So that works pretty well. But we also see there's going to be different applications, which we're going to go into next, which is the honeybees. The honeybees, I think, are very cool. So similar to the rabbit problem, these honeybees, you can track their populations through generations. It's very similar to the rabbit problem, although biologically they're not the same as rabbits. Rather than a pair of bees just making another bee or another set of bees as the rabbit problem, male bees are born through unfertilized eggs, and the female bees are born through fertilized eggs. So only the queen is the parent of males, but females have both the queen and a father honeybee. But it doesn't really matter to the recurrent sequence because it still solves it. If we look in this table, the males start out with 1, the next generation will have 0, and then 1, and we see it begins to add. Now, I could have continued this much more, but I think you guys get the vision. The female also follows a very similar formula, and the total will follow the same exact formula. Um, so not only do the total follows, but the male and the females both follow. Um, so going on, we still have more with the honeybees. I know we love honeybees. Uh, they obviously love the Fibonacci sequence as well. Real math guys over here. Uh, Another thing you can look at with the honeybees is that if you set two infinite honeycombs, which, like as shown in this picture here, um, if they can only go one direction, which is right, which is how they usually work, how many paths can they take to each one? Now, to go to number one, obviously there's only one path. They can just go to number one. Now, to go to number two, they can either go directly to number two or they can go to one through two. So there's two different paths there. For three, they can go from one to three, from two to three, from one to two to three, which is three total paths. And as you can imagine, four is going to have five total paths. And we're going to get that same recurrence formula that we saw with both the rabbit problem and the previous tracking of generations of bees. So we find this recurrence formula repeated in different ways in nature, especially in these biology forms. But biology is only so exciting. Let's go into finance, stuff that, real dudes care about. The finance bros also have their share of the sequence. Thanks to Ralph Elliott, who quote unquote found this theory of recurrent spikes and dips within the market, as we can see in this image on the right. Um, this is only applied to the whole market, or known as the S&P 500. They follow the same pattern according to Elliott and can be tracked as such. It depends what time frame you're looking at it, what scope is going to count how many waves there are. So the closer you get in, there will be more waves and dips. The farther you go out, they'll look much greater. But no matter what way you look at it, according to Elliott and his theory, is that it's going to follow that same recurrent sequence. Like looking at this diagram, we can look at each size. The smaller ones have much more, but they're counted in the bottom right. These are Fibonacci numbers, and we'll follow that recurrent sequence. To this day, people still use this, although I would not recommend this. Like, do not go into the stock market and start counting the amount of spikes. There are an infinite amount of factors that go into this. And, I was looking up research and there's really nothing that points to this being fairly accurate. It's known as a 50-50. So there's not really anything proving that this is true and it's going to make you millions of dollars. But there are people on YouTube day by day, every single day, that do track this and record what they have found. You can check them out. Pretty cool. I don't know why they're doing it, but just in case, maybe something does come to light regarding this. But I think the most applicable one, at least to our lives, is going to be the stuff in computer science. And for this, we have to know what heaps are. So heaps are in data structures. They're usually shown as trees. They usually follow binary paths and values. The property of heaps are that each parent node, as shown on the right here, must be greater or equal to its children. And they're built for insertion and deletion in data structures. But an advanced form of these heaps are known as the Fibonacci heaps. And these data structures are used for optimizing queues, but they do not follow that same parent node property. They can be bigger or smaller than their children, but they must stay consistent. So if they are going to be bigger than their children, they must always be bigger. And if they're going to be smaller, they must always be smaller. So this one's shown here. This one would be known as a minimum Fibonacci heap, as the parent nodes are smaller than both of its children. And these Fibonacci heaps are used in graphing algorithms, shortest path problems, and network flow algorithms, really just trying to optimize stuff. And is often used in dynamic programming as well. So we have the honeybees, the stock market analysis, although it's a little bit iffy, and the computer science, which is very applicable. This is all because of Lucas. Lucas, without him, we would not have what we have today from the Fibonacci sequence and the recurrence formula, because he pretty much he pioneered this analysis by himself. And thank you for watching. Thank you for Edward Scissorhands and Lucas over here. Have a great day. Take care. Thank you for listening.